Scientific measurements are reported in a very specific way. We record all the digits that we're certain about and one digit that's estimated. I'm going to skip that example because I don't think it really helps that much. So here we have a pistachio on a little kitchen scale. And we're going to weigh this, and we want to know how much it weighs. We're going to ignore the ounces side because we're doing science. We're going to use grams. So we look over here, and we first have to just kind of orient ourselves to that scale and say, well, what are these lines meaning? Well, this one's labeled 10, and that one's labeled 0, and it says grams. So that line must be 0 grams, and this is 10 grams, and there are 10 divisions in between. So that means that each division represents 1/10 of a gram. No, 1 gram, sorry. This is 10, and so each of these lines represents 1 gram. That makes sense? So we look at this red line here. Is it red or black? It's black. And we see that it's between 1 gram and 2 grams. So when we write down 1 gram, is there any uncertainty in that? No. There are actual lines there. It's between those lines. It's at least 1 gram, and it's not more than 2, right? It's less than 2. There is no uncertainty at all. But instead of just calling that 1 gram, we can estimate, even though those lines are really close together, we can estimate between them. Are we always going to be right? Are we going to agree? No. There's uncertainty there, but we can still get information. So we look in there and we kind of mentally divide it into 10 pieces. And we say, well, that's really close to the 1. It's definitely less than halfway. I'm going to call it 1.2 grams. Someone else might read that and call it 1.3 grams or even 1.4 grams. And we will agree to disagree about that last digit because it is estimated, it is uncertain. So the idea here, and this is important, we'll be doing this in lab, and once you get the hang of it, it's easy, but until then, people screw up a lot. To help us remember, we say read between the lines. So that means between the lines on the scale, we're going to read between them. We're going to estimate between them. So we see that the markings are every 1 gram. We're going to estimate the next decimal place. Any questions? We've got some thermometers over there. They have 1 degree markings. So we can tell to 1 degree for certain, and then we estimate the 10th place. On most rulers, there are 0.1 centimeter markings. We read between the lines and estimate 0.01. We estimate the second decimal place. Do a couple of examples here. So here's a thermometer. It's in Celsius. That part of the thermometer is cut off. And so we're supposed to record the temperature here. So here's the green alcohol part, and we're supposed to figure out, it doesn't show very well, but it's right there. We're supposed to figure out where is that on this scale. Well, here is 100, and that's 110. So what does each individual tiny line represent? It's 1 degree Celsius, right? So that means we need to estimate to the 10ths of a degree. So we're going to look at this and see where it falls, and it looks like it's right here, maybe slightly above. Would you agree with that? So that's 103. So I'm going to write that this is 103, and then I need to estimate the next decimal place. Sometimes you look at it and you think, I think that's right on top of that. I think it's right on 103. I still need to estimate the next place. So if I think it's right on, I say 103.0, and then I write the unit degrees Celsius. Somebody else might look at that and it's a little higher. I'm going to call it 103.1. Both of those are valid readings. Any questions? Here we have a liquid in a graduated cylinder. And the surface of the liquid is curved. That's called a meniscus. And we'll learn later in the semester why it does that. Glassware like this is designed to be read to the bottom of the meniscus. So there's this dark thing here, the curve of the surface. We're going to read the bottom of that. So we look at this graduated cylinder, and these are milliliters. There's 3 and 4 and 5 milliliters. So each of these lines represents 1/10 of a milliliter, 0.1. So we look at this and we say, well, there's 4 and there's 4.5. This one's 4.6, but it's not quite that far. Do you agree with that? So it's 4.5, and then we need to estimate, because it's clearly above the 0.5. So you look at that, and what do you think it is? Somebody be brave. 4.56. 4.56. That's fine. Anybody else? Okay, 4.53. That's not necessarily wrong, but what we're trying to do is we're looking at this piece right here and estimating how far it is between these. To me, it looks like it's more than halfway, right? So if it's up here, this would be 4.6, and this is 4.5. So I think 4.53 is maybe a little low. I might call that 4.58, because I think it's a little closer to the 6. But that last digit is uncertain. It's not useless, though, and so we keep it. And scientists all understand, we write a measurement, the last digit is always uncertain. Any questions? You can't measure anything exactly. It's disturbing, but it's true. So when we report these measurements, we need to be careful of how many digits we report. Just reading it off of a measuring device isn't a problem, but when we do math on those numbers, then crazy things can happen. Like we found that temperature had 0.77 and the 7s would go on forever. Well, how many of them do we keep? So significant figures is a technique used to preserve the precision of a measurement during calculations. Precision is how precisely, how closely we know the answer, the measurement. So significant figures is not the most robust way of doing this. It's better to use calculus, but I don't think anybody here wants to do that. And so this is actually a much simpler, faster way than using calculus. So we define a significant figure, sometimes called a significant digit, as non-place-holding digits in a recorded measurement. They're going to include all of the certain digits and that one estimated digit. If you have more significant figures, you have greater precision. If you have fewer, you have less precision or less certainty about the measurement. So, rules for counting significant figures. All non-zero digits are significant. So you look at any number that's written correctly, any digit that isn't 0, that's a significant figure. So it's just the zeros that are going to give us trouble. And boy, do they give people trouble. There are 3 kinds of zeros. There are interior zeros. I sometimes call these trapped zeros. These are zeros that are between other non-zero digits. Okay? Those are always counted. Then we have leading zeros. Leading zeros come at the beginning of the number. These are never significant figures. All they do is they serve to locate or hold the decimal point. So here we have 0.00023. These are leading zeros. They're coming at the beginning of the number. If we got rid of them, we wouldn't know where the decimal point went. So we need them, but these numbers do not reflect measurement. 0.04268. Those are leading zeros. We're not going to count them as significant figures. Okay? Then we have the trailing zeros. Trailing zeros come at the end. I explain this in my lecture slightly different than the text does. It'll give you the same result though. If you like the text explanation better, go for it. So trailing zeros, sometimes they're significant, sometimes they aren't, and this is where it really gets confusing sometimes. So trailing zeros are significant if there's a decimal point written in the number. So here we have the number 39.0. So that 0 is a trailing 0. It's just at the end of the number. There is an actual written decimal point, and so then we're going to count that as a significant figure. 120.00. There's 3 trailing zeros there. There's a written decimal point. It doesn't matter where the decimal point is, but that it's actually written. Here's a number, 300. That has 2 trailing zeros. There's no decimal point there. If there's no decimal point, then we can't really tell. It's ambiguous. We can't really tell what the writer of that number meant. So we try to avoid doing that. But when we encounter it, we say, well, just to be on the safe side, we'll assume the worst. And so we will assume that those are not significant. So over here, 1.432000, trailing zeros, there's a decimal point way up here, but those are significant. Any questions? What do the numbers represent? These are just made up numbers. Yeah, just to give you an example of what kind of digits we're talking about.
So if there's no decimal, for example, 300, the 2 zeros at the end would be insignificant, but looking at 39.0, that 0 would be
Correct. Yeah, so for this number 300 without a decimal point, we'd say it only has one significant figure, the 3. 39.0 has 3 significant figures because there's a decimal point, and that decimal point makes the 0 significant.
But if, for example, you had your 300, what if there was a decimal right after the 0?
Excellent question. 300 and then write a decimal point. There's a written decimal point, those zeros are significant now. It looks a little weird though, doesn't it? So we don't usually do it that way. But the written decimal point makes it significant. Any other questions? So let's practice a little bit here. Oh, forgot about this one. Exact numbers. There are some numbers that are exact. And so how many significant figures would they have? Well, I guess you could say it would be infinite, right? Because they're exact. And examples of this, counting of discrete objects. So how many Sharpies am I holding up? 2. Are you sure? Is there any uncertainty? Is it 2.5? Maybe it's 2.3. No, it's exactly 2, right? These are objects that can be counted. You count the number of people in the room. It's exact, right? So if we're going to use that number and we want to know how many significant figures it has, we say, well, it's exact. Or if you pressed for a number, say, well, it has unlimited or infinite significant figures. So that's one example of an exact number. Integral numbers that are part of an equation. So the diameter of a circle is 2 times the radius. This number is an integer that's part of an equation. The diameter is exactly 2 times the radius. Okay. Also, defined quantities. So, you look at a liter is 1,000 milliliters. Well, those numbers are exact because we defined it that way. An inch is actually exactly 2.54 centimeters because they redefined the inch just a smidge so that it would be exactly 2.54 centimeters. Some conversion factors are defined, others are not. So if you are within the metric system, like milliliters to liters or something like that, those are all by definition, those are exact. If you're within the English system, inches to feet, how many inches in a foot? 12, right? Are we sure? Yeah, it's exactly 12 because that's how the system was set up. So those would be exact numbers. So let's practice. How many significant figures in each number? So 554 kilometers. 3. Barrington needs zeros. 1.01 times 10 to the 5th meters. 3. This number is written in scientific notation, where we've factored out a bunch of tens. The times 10 to the something is what's holding the decimal place. So the times 10 to the something is not, those aren't significant digits, but everything in front of the multiplication sign is. You'll always have a decimal point with any zeros. So here we have a trapped zero. We have 3 sig figs there. 1.4500 kilometers. 5. We have trailing zeros, but there's a written decimal point, so we're going to count those zeros. 7 pennies. Is it 1? It's exact. Okay? That's an exact number. You can count 7 pennies, and there is no uncertainty. So if we needed to know, well, how many digits could we express that to? I mean, I could write 7.000000. Stop me when we get to where we're uncertain. You could just keep going forever, right? So it's an exact number or an infinite number of significant figures. Okay? 0.00099 seconds. 2. We look at the zeros. Those zeros are at the beginning. Don't count them. Doesn't matter if this is a decimal point. If they come at the beginning, they're not significant. They're important, but they're not significant. So just the 9 and the 9. 21,000 meters. 2. Technically ambiguous, but we're going to assume the worst, 21,000. Because if there's uncertainty in that ones place, that means that this is measured to the nearest 1,000 meters. And so we're saying at 21,000 meters, well, this is between 20,000 and 22,000 meters. If I put a decimal point here, that makes those trailing zeros significant. And now I'm saying it's measured to the nearest 1 meter. It's 20,999 meters to 21,001 meters. Very small, right? So how we write the number establishes the precision of the number. We'll get a lot of practice with this in our worksheet today. So when we do calculations, we should not gain or lose precision just by multiplying or dividing. And so we have some rules to keep track of the significant figures so that doesn't happen when we do the math. So there are 2 types of operations that we'll learn about. Multiplication and division are related. They're essentially opposites of each other. So they share the same rule for significant figures. So when you're multiplying or dividing, the result, the answer, has the same number of sig figs as the factor, the thing that you were multiplying or dividing, with the fewest significant figures. So 1.052 times 12.503 times 0.53, and you get this on your calculator. We're going to look at each of the numbers that we were multiplying and identify how many significant figures do they each have. Well, this one has 4, this one has 5, and this one only has 2. That leading 0 doesn't count. And then this is the tough part. Which number is smaller, 4, 5, or 2? 2, this one. This is the smallest, so then we need to round this number so that it has 2 significant figures. Here's an example of division. 2.0035 divided by 3.20. That's the answer you might see on your calculator. We're going to look at these numbers and count the sig figs. This one has 5. This one has 3. 3 is smaller, so we're going to take this number and round it to 3 significant figures. When we're adding or subtracting, these are a different type of operation, and so we need to treat the sig figs a little differently. So here, the answer, the result carries the same number of decimal places as the quantity with the fewest decimal places. So here, multiplication, division, we're looking at the fewest significant figures, adding and subtracting the fewest decimal places. So I have a couple of different ways I can explain this. I'll go through it real quick here, and then if you need some more clarification, I'd be happy to go over it with you for 3 hours in lab if that's what it takes. So if we're adding these numbers, just add them on your calculator, write down what your calculator gives you. We can do this in terms of counting decimal places by looking at how many decimal places does this number have? Well, this has 3 decimal places, right? There are 3 digits after the decimal point. This has 2 decimal places, and this one has 4 decimal places. Well, the fewest decimal places is 2, so I round my answer to 2 decimal places. So that's the rule. Let's think about why the rule works. When you record a number, you record all the certain digits and the first uncertain digit. So in this number 2.345, it's the last digit that has some uncertainty, right? And in 0.07, it's the last digit that has uncertainty. And in 2.9975, it's the last digit that has uncertainty. Everybody okay with that? Because that's how we write the numbers. When we add these together and we get a result, we want to include all the certain digits and just one uncertain digit. The rest of that after that are just garbage, really. So when we're adding here, if we were adding by hand, don't do this because people screw it up so much, but just think about the process. We would understand that to add, we need some digits in there, right? And so we say, well, we don't know anything about it, we'll put zeros in there. And so you add the columns, right? So here I'm adding a 5 that I'm not sure about to some zeros that I'm just like made up. Is this 5 down here certain or uncertain? It's uncertain, right? Because I wasn't even sure about this 5. And then I added, I don't know what to it. It's uncertain. So this next column of 5, an assumed 0, this 5 is uncertain, and we're sure about the 7. So I add those and I get 12. I'll carry the 1. Am I certain about that too? I can't be because I was adding a 5 that I wasn't sure about. Maybe it's a 4. Maybe it's a 6. So can I say that the sum is 12 for sure? I can't. So this 2 is uncertain. That makes sense? Then there's this line here. I'll explain why that line's there. So here I've got a 4. I'm certain about the 4. Not sure about the 7. Certain about the 9. Because there's one of those things that I'm adding is uncertain, then the result is uncertain, right? So this 1 is uncertain. Now I get over here, a 3. Am I sure about that 0? Yeah, it's not counted as a significant figure, but I know for sure that it's a 0. So I've got 3 and 9. That's going to add up to 12, but then I've got those other digits carried over. So I'm certain about the 4. I'm certain about the 5. I'll be certain about everything to the left of that. When I report this answer, I want certain digits plus 1 uncertain. So the 5 and the 4 are certain. The 1 is the first uncertain digit, and that's where I'm going to stop the number. Does that make sense? So let's look at this one. Here's a subtraction. Do the subtraction on your calculator. You get 679, sorry. Another way to do this, instead of counting decimal places, stack them up like this as if to do it the long way, and then look which of these numbers stops the soonest. Well, the 9 does, so I'm going to draw this line to the right of the 9, and that's what we did over here. Let me erase the messes that I made. This line is drawn after this 7 because that's the number that ends the soonest. It's got the fewest decimal places. So we draw that line there, and that line is going to tell us where we should round. So this tells us we should keep the 6. We have to round up because the next digit is 7, so we'll call this 5.7. This number has 1 decimal place. This has 3, so the answer is rounded to 1 decimal place. questions?
What if there's like 305 and there's no point? So there's.
That's a good question. What if there's 305? Like if it was, oops, can't write with the eraser. Like if we had 305 in there. So 305 in here, the 5 is uncertain. It has 0 decimal places. And so then if we're drawing a line to figure out, having an argument with my iPad, we'd have to draw the line there. And so then that's going to chop it off at the ones place. So when we work on examples of this in our worksheet today in lab, I want you to work on understanding why you're getting the correct answer when you get the correct answer. Okay? When you understand it, it's easy. And today is the day to figure it out, okay? I am willing to explain it to you over and over in multiple ways until it makes sense to you. You are all capable of understanding. You just have to want it bad enough. Rules for rounding. So you round down if the first digit is less than 5, 4 or less. You round up if the first digit you're dropping is 5 or more. So this is something you should have learned in elementary school. We're not going to do that odd even thing. We're just going to go 5 goes up, less than 5 goes down. It is very important that we don't change the overall size of the number when we round something, the magnitude. So if we're rounding and where we're rounding is in the tens place or the hundreds place, we have to be careful. Okay, I'll show you an example. So let's say, we have a little rental house and $125,473. We're going to round this to the nearest hundred. Well, where's the hundreds place? What digit's in the hundreds place? The 4, right? This is where the hundreds are. So to round, I'm going to look at the next digit. It's a 7. 7 is 5 or larger, so I'm going to round up. So I'm going to round this to a 5. I'm going to keep everything out here. And I'm going to buy that for $1,255, right? No. You can't just round a number and end up with something that's 100 times smaller. I can't just drop the ones and the tens. I would need to put place-holding zeros in there so that this is still 125,000. So it's rounding to the nearest 100. We're not going to change the overall size of the number. So anytime, if you're doing the ones place or anything to the right of that, you're good. But to the left, people get into trouble. Okay, so just watch out for that. The best thing to do is to put the number in scientific notation first and then round it, and you'll never get into trouble. I'll just talk about a couple of these. So here we have 5.34. We're going to round to 2 significant figures. We're looking at the 3. The next digit is 4, so that number is closer to 5.3. 5.35. We're keeping this first digit here, the 5 and the 3, and the next digit is 5 or greater. We round up, and that's going to be 5.4. This last one, 5.349. That 9 has nothing to do with anything. We are only going to look at the first digit that we're dropping. So we've got the 5.3. Sometimes it's helpful to do this. Underline the last digit that you're going to keep, and this is the one we're looking at. That's less than 5. I round down. Sometimes students get a little exuberant and they start at the end of the number and they round up and down all the way back. Yeah, it's too much work and sometimes gets you the wrong answer. Any questions? It's common for us to have to do multiple steps in a calculation. You may have to add something and then multiply and divide and do all kinds of things. It's important not to round each individual step. You want to wait till you get to the final answer and then round. If you're fairly good with a calculator, you can often do calculations like this without writing down any intermediate values, and that's the best thing. When you do need to write down intermediate answers, keep track of the significant figures, and my rule of thumb is you don't have to write all of them, because sometimes your calculator will give you like 9 digits and most of them are garbage. Just keep 2 extra digits. You keep 2 extra digits and you'll be good. That's when you have to write down intermediate values. So let's look at this example. 6.78 times 5.903 times 5.489 minus 5.01. So here we have multiplication and subtraction. We can't apply one rule to everything. We have to look at the operations separately. So if you do the part in parentheses here first, like you should, you end up, your calculator is going to tell you 0.479. Calculator doesn't understand sig figs. We need to look at this and say, oh, we're subtracting. We're going to go with the fewest number of decimal places. 3 decimal places, 2 decimal places. The result in the parentheses then has 2 decimal places. I'm going to underline it. We often underline the last significant digit. It's the uncertain one. I'm going to keep the 9 around though, because I'm not done. And then I've got these other numbers, and now I'm going to multiply. Now I've got all multiplication. I do the math, I get 19.1709, and then I look at significant figures. So 3 sig figs, 4 sig figs. This one only has 2 sig figs, 0.47. The 9 we're carrying around, but it's not a sig fig. We stop at the underline. So then our answer is rounded to 2 sig figs, and we report it as 19. Any questions? You don't. If you wrote a decimal point after the 19, like that, it wouldn't change anything. Yeah. It looks a little silly. It's not necessary, but it's not wrong. The decimal point there would matter if you had a 0. Then it would be important. Okay, let's do a couple of examples here. In the interest of time, I'm just going to do the last 2. So let's do letter C on our calculators. 2.5110 times 21.2 divided by, and you can just use the parentheses, open parentheses, 44.11 plus 1.223, close the parentheses, equals, oops, my calculator is showing me a mess. 1.74, 174, 270,399. Anybody else get that? Okay. That's a ridiculous number of digits. What operations do we have here? We have multiplying, dividing, and adding. So we have to look at them separately because they have different rules. So this adding, we can add those together and figure out, well, what is the intermediate there? 44.11 plus 1.223. The only reason we need this here is to keep track of significant figures. When I add, that's what my calculator gives me. I need to look at which number has the fewest decimal places, and that would be this one. It's got 2 decimal places. So this intermediate result here has 2 decimal places. Okay? Then in my calculator, I took this number and that number and did multiplication and division. Those use the same rule, and so we can lump them all together. There we're looking for the number with the fewest number of significant figures. So how many sig figs in 2.5110? 4. No, sorry, 5. 5. I can't count today. There's 4 decimal places. How about 21.20? 4. And this number, 4. That 3 is the last significant figure. Don't count the last 3. So 4 is the smallest number of significant figures, so that's what I'm going to round my answer to. So there's 1 place, 2, 3, and the 4. So this is the 4th significant figure. That's where my number is going to stop. I'm going to look at the 2 to decide, do I round up or down? And since that's less than 5, I round down, and the result is 1.174. Any questions? Let's do this one down here real quick. 12.01 times 0.3 equals plus 4.811. So my calculator is telling me 8.414. I have multiplication and adding. So I have to look at those operations separately. So here I have multiplication. When I multiply that, 12.01 times 0.3, that gives me 3.603 is the result in parentheses. How many significant figures does that number have? Should it have? Well, this one has 4 sig figs, this one has 1. So then this number only has 1 significant figure. Okay, 1 significant figure. Now I look at this number and that number. When I'm adding, I'm looking at decimal places. This one has 3 decimal places. With this being the last significant figure, how many decimal places does it have? 0. It ends in the ones place. So that tells me that my answer here has to end in the ones place. And so I'm going to call that 8. Okay, we'll get some practice on the worksheet today. Accuracy and precision are 2 words that we'll use a lot in lab. Accuracy refers to how close to the measured or to the true value you are, and precision refers to, well, you're taking a bunch of measurements. How close together are those measurements? How reproducible are they? We can look at some student data here. They've got a lead block that weighs 10 grams, 10.00 grams, and these students are weighing it. They're each doing it 4 times, and they're reporting their results. So when we look at this table, we're like, it's hard to see anything from that. That's why scientists graph things a lot, because it makes it more visual. So same data as bar graphs. So here's student A, and we've got the different trials, and we have bars to represent the mass that they got for each trial. The blue line here is the true mass. And the red line, the red dotted line, is the average of their measurements. So when we look at this student's results, the average is quite a bit higher than 10, so not very accurate. When we have a true value that's 10.00 grams, where's the uncertain digit in that number? It's the last one. So we should be able to come to a value that only differs in the second decimal place. And here the average is 10.13. That's differing over here. That's not very good. So this is not accurate. And then we look for precision. We look, well, how close together are these different measurements? They're all over the place. So not precise. Not accurate, not precise. Student A failed. Bad. Okay, here's student B. Got an average of 9.79 grams. Is that close enough to 10.00? No, not very good. Not accurate. But when we look at these measurements, they are all very close together, right? very precise. So this student is very consistent and reproducible, just wrong. And then we have student C. Student C came up with an average of 10.01 grams. So in that number, they're saying that the uncertainty is over there, and the true value, 10.00, has uncertainty there, and those are close, 0 and 0.1. 0 and 1, we would consider those numbers to be the same. The student nailed it. And then we look at how close together are these numbers. They're very close. Okay? So accurate and precise. That's what we're always trying to get, is accurate and precise. Can't always do it, but that's what you aim for. There are two kinds of error. There's random error and there's systematic error. So student A had random error. There was not good precision. Random error has an equal chance of being high or low, and so it scatters all over the place. You can get rid of random error by making multiple measurements and then averaging the result. That will get rid of random error. Systematic error is where the error is always or mostly too high or too low. So you could get very precise results with some systematic error, but your actual result will be too high or too low. So when we have results that deviate from what we expect, we need to look and see, well, what kind of error is going on here? If it's systematic error, we can probably do something to fix it. Maybe the balance was calibrated incorrectly, or maybe you're not using it right. And so you fix that issue, and then your results will be better. With random error, sometimes there's things that you can do to cut that down, but a lot of times what you'll do is I'm going to just make a bunch of measurements and average them so I can get rid of the random error.